Hello,
Yes, sir. Good afternoon.
good afternoon. Okay, there are not many students today. Any reason? Cricket match? Is that so? So, how many of you are watching cricket match? Nobody. Anybody watching this one day match that's happening between India and Australia? Okay. All right. So, shall we wait for people to join in or shall we stop? What is the reason? Pavitra, can you please take attendance and then send a stinker to the people who have not come today? Uh, Also, I think we can mark a copy to the head of department such that if they get minus 10 marks, they shouldn't cry at the end.
So I'll take the attendance now.
And can you just notify them? So, and mark a copy to me so that we will minus 10 those who are not there in the class.
Okay, sir.
Okay.
Yes.
Please note, and in fact, many of them have been absent quite a while. So, if they fail, then I don't think I will be lenient. Otherwise, see, attending see, last two batches have done very bad in industry, right? Recently I have got a note from a company, of course, it's for mechanical engineering department, that they were surprised at the performance of our students who just couldn't answer simple question and they have selected zero. Okay, that clearly reflects. Of course, this is all about your seniors. They clearly reflects non-seriousness, and your batch is comparatively more serious than last two batches. And if studying in IIT, if you get 4 lakh rupees kind of job, then it's really shame, right? And many of your seniors have got that. I mean, you should compete with the best of the best. The what is the difference between you and somebody in say MIT or Berkeley? Absolutely no difference, excepting that people are more attentive there in classes and they're regular because they pay from their pocket. Uh, okay, so I request you to be please be sincere. Not always you get everything for free in life, right? So you'll have to make an effort. Okay, all right. So request you to please be attentive in the classes now or also in future, and please try to take these courses. When you are doing online, take best advantage of it. Never take it on mobile. Take it on laptop, right, or iPad at least. So you have bigger screen available for you to understand. I mean, some certain things you can do to increase your grasp. Okay. Uh, Otherwise, I don't want any one of you to struggle getting a job less than 15 lakhs. I'm not joking. There are plenty of companies, and many of them don't come to ITs primarily because our students don't join them, but they all pay more than 15, 20 lakhs. Okay. So, request you to please be attentive in classes and okay, all right. So this topic is very important, and I hope you would have got some time to go through it. If not, please, uh, go through it, and then feel free to ask me any question if you really want. If you have difficulty in understanding, I can take the class n number of times, and could be as high as 10. Okay. Same thing I can repeat for you, but you need to make an effort. Okay, all right. So the so we'll try to finish this chapter on virtual memory tomorrow, and I have expanded this lecture from basically 2 hours to 3 hours now, essentially because I think that is the most important topic that we are studying in general in computer architecture, right? So memory hierarchy, cache memory, and now we are uh, looking at virtual memory. So this was a case some 40 years back. We have CPU directly accessing the main memory. Okay, and this is not a good model because programmer has to know where all the program sits and what location the program is reading, right? And then each CPU or each process that runs on CPU has vision of a virtual address or virtual address space, or we call it address space. Okay, and then this address space is fine if it's only one process running on a computer, like in embedded systems, etc. But if there are hundreds of processes running, then each starts with 0 to some number n, then all of them have to share this main memory, and which is a very difficult task, right? uh, so we have seen this, that each process having an address space, and this each process then has to, when it's running on CPU, it has to share the physical memory, right? That's possible only if we have some mechanism in between. So the mechanism that we call is actually virtual memory. Okay, so basically each process have vision or can assume that it has whole address space available, and this address space available in the main memory. Okay, uh, all right. So right now we are not. We will also look at how a cache is included in the whole game. Uh, but in general, the assumption is that process knows that whatever it wants is available in main memory. Okay. Now when we started looking at the pipeline, and when pipeline data path, then we have seen that within one cycle we have requirement of instruction to be available, and also instruction you know uh, to be similarly instruction to be decoded, and register fetch has to happen. Okay, so so it means that the time available for each instruction to be read uh, and register fetch to happen is usually less than a cycle. It means that our time available for instruction read is less than cycle. Similarly, when we are writing something, that's a last but one phase, memory phase of pipeline. Again, writing has to be done in less than a cycle, and you know that main memory takes more than 1,000 cycles. So obviously there is a need for cache. Okay, so we'll come to that little later. Right now, you hold on to that question, and just let's complete it with a view of that. We have processes. Each process has a address space, and then whatever process wants is available in main memory. Now the address space could be very large. Okay, like for 32-bit machine, it's 2 raised power 32 uh, address space. For 64-bit machine, is 2 raised power 64 address space size, and page size is usually 4K. We have seen that virtual address space we partition into pages. Okay, similarly, physical memory is also partitioned into pages, and each page size is 4K. Now, this 4K has been possibly there for most of the machines now, because 4K gives 4 kilobytes gives sufficiently large page size for considering we have temporal and spatial locality. Okay, now this is the unit of transfer between secondary memory, that is disk memory, and main memory. All right, now if suppose we have thousands of pages in virtual address space, we need not have everything in main memory, because main memory anyway is shared. And secondly, not every part of the address space we may be using. So basically the parts that we are going to use can be usually is brought into main memory. Okay, we'll see how it is brought. Okay, it means that number of processes like P1, P2, P3, they have their own virtual address space, uh, uh, shares the main memory. Okay, like here different pages are mapped to uh, different pages are being used by this process, and in order to map from virtual address space to physical address, we have something called page table. This we have studied last time, right? So for each process we have a page table, and this page table starts at certain address. That address is, suppose this process right now is under in execution. Okay, then this page table, start of the page table will, this address is available in a register. Okay, we'll look at that, right? So as soon as process is brought into execution, the OS loads, OS then points out to the start of the page table, and in order to that, OS loads this register, some register with the address, start address of the page table. Okay, and then we have seen the method, uh, this method of address translation. The instruction, I mean, in pipeline we have seen instructions, instruction execution. For example, we have seen load and store. So load word to some register, say S1, bring a data from some location that's pointed out by this. Okay, so this address that we generate is virtual address, is 32-bit address, right? Now this address is available to us here. Then we know that we are partitioning the virtual address space in number of pages. Okay, now this virtual address space and pages is just a concept. Okay, so we say that each page is of 4K. Is basically we then we need 12 bits to represent this. Okay, so then 12 bits represent page offset, which location within page we are referring to, because we are using byte addressable memory, and remaining 20 bits we use to represent page. Okay, now the offset, we don't translate offset, we translate only virtual page number to physical page number. PPN is physical page number, right? Or virtual address space or virtual memory that's visible to a program to actual page in physical memory. Okay, obviously number of the physical memory size smaller, the number of bits will be lower. Here we assume that 15 plus 12 to raised power 27 is the size of main memory. All right. Any question up to this point? Okay. Is it clear?
Yes, sir, it is clear at least to me.
Okay, thank you. All right, so now after we have, okay, all right. So after that, we have seen that these pages, virtual address space or something that process a view of at the time of execution, okay, is something that we have seen, the stacks that we have seen, a stack, heap, etc., right? So there's something at the runtime that structure is available, or that data structure is available, right? And then not everything of that has to be there in main memory. Okay, because main memory is limited, only that something that is in use has to be there. For example, your program consists of say 50 such pages. 50 into 200K size is your program size. Okay, each so 50 pages are there corresponding only to your code, compiled code, right? Or bind or machine instructions. Okay, and not everything you are executing, because there is always a locality, but we have to keep that somewhere. Where are we going to keep that? Okay, we are not keeping it in main memory because limited, then we are keeping it in secondary memory, which is mainly disk memory. Of course it can also be flash, but right now we are assuming it's disk memory. So something that program needs at the time of execution, or some we have seen this structure where we have stack and heap, uh, and text area, etc. All this will be kept in disk memory. Okay, and we call this a swap space. Somebody has asked this question, what is swap space? And we said, okay, we'll answer it when we study virtual memory. So this is a swap space, right? Something at the time of execution of program, something that's or image of that data structure available in disk is called swap space. Okay, is it clear? Okay, so it has three kinds of pages. Obviously that this is also split into pages. Okay, it has three kind of pages. One is unallocated, means that these pages, because address space is a very large part of that space is unused, it means that these pages have no meaning, so it's unused. And then something is cached, it means that these pages are available in main memory. Okay, and something is uncached, it means that main memory does not have this part of address space for a process, but it's available in swap space or secondary memory. All right. Is this clear? All right.
Yes,
Okay.
sir.
Okay. Let's go ahead. Huh? Uh, now what we have now concept of page table we have studied it last time. Okay. So page table. Just a minute. Okay. Page table maps virtual address to physical address or uh, virtual pages in disk memory, right? So it's something like this. Okay. So okay, so we have some pages that are mapped to, some entries here which we call a page table entry um, in page table, okay, are mapped to physical memory. It means that these pages are available in physical memory, and if there is a reference to any location in that page, this means when we say load word something, this, and when we say load word and this address, this corresponds to a byte, right, or word, 4 bytes. Okay, then that, if that is available, then we will for example is available in page table entry 1, then it will point out to corresponding physical page from where we can read this word. Okay, if it is not available, then it means that there is two possibility. It means that it is non-existent as part of address space, or if it is existent, then it will be in the disk memory. All right, note that we have written that this page table is also memory resident, is also part of DRAM. Okay, and then main memory is also DRAM. So what will happen if when we have instruction, say load word executing, it will give the virtual address, and based on virtual address we will find out virtual page number, and virtual page number will basically will use as an index to point out to this address page table. Okay, and then we will look at the physical address and go here to main memory and read corresponding word, say for example from the, so actually they are what in order to reach every word we are spending 2 times read, right, from main memory, and each is taking 1000 cycles. So overall number of cycles we will take for simple read is 2000 cycles minimum. Okay, and what happens if it's not there? For example, right now we assumed it's there. If there is a, if there is access to this a location which is part of this page and it's not there, then we'll have to bring it from disk, and then number of cycles will be 1000 times thousands. Okay, few million cycles will require before this page is brought into main memory. All right. Okay, let's with this knowledge let's move ahead. Okay, this we have studied last time, so let's move ahead. Now there are two possibilities when we have virtual address that's coming, say for example load word, uh, say S1, some displacement, and say S2 for example. Okay, so this gives a virtual address, so we get the virtual address from there, and the part of virtual address we have seen earlier is VPN, virtual page number, and offset. All right, so we get the virtual page number. So this points out this is nothing but virtual page number. Okay, and we use this an index, and we know the starting address of this, so we can always find out the location. And in this entry we see if the valid bit is 1, it means that page is available. Then okay, and then we can read this page physical page number, and can go there and read corresponding address. We know now the starting address of this one page, and then the offset, this offset field, part of this offset, you use the offset to come read the exact location. Okay, so that's the thing. uh, so something that we call it means that this virtual address, when we reference in page table and know that page is available, we call it the page hit. It means the page is available in physical memory. Okay, now second possibility is that page not hit. It means that page is not available. For example, this one. Okay, so okay, for example, if sorry, uh, it refers to a location here which is not there, then is a page miss. Okay, so we look at that situation here. Okay, so we call it page miss or page fault. It means that that address that we are referencing is not available in physical memory or main memory, right? So for example, now we are referring to as a part of say load word, say S1, some displacement say 10 and S2. This address we are referencing to, and part of this is virtual page number. Virtual page number we take to reference, and we find out valid bit is 0. It means, and it is non-null. Null means that it's non-existent. It's non-null means that it exists. Then we'll read this address, disk address from here, and we call this situation is a page fault. Okay, now when there is a page fault, then OS is asked, basically we'll this is special situation. Now OS will be asked to bring this page from secondary memory to main memory, or disk memory to main memory. All right, so now this handler, page fault handler, will know that this page is here in secondary memory. It has to bring it to physical memory. All right, okay. uh, Now in order to do that, okay, it has to, we remove one of the pages because the physical memory is full. Okay, so it can use some algorithm, say for example LRU, or one of those list use, or some of these, to choose one of these, it can be evicted. Okay, note that this memory here is kind of fully associative memory. It means any page can go anywhere, right? Any of these pages here can go at any of the locations. So it has to choose which one to evict, or to be removed, right? Such that a new page can be brought in. So it uses whatever algorithm. Let's assume that uses LRU or some other algorithm. Okay, and then it has to bring the page, this page, to this location. Okay, all right, and simultaneously it has make the change in this value here, and make a valid bit as 1. Okay, now note that at this point in time, when there was page fault, the whole thing is stopped, right? It means that the pipeline is halted, okay, or stalled. And then when this page is available, then OS will again give control to the pipeline, or pipeline will start, and then again there will be reference made to the same address, and now there will be hit, and as a result of that, the word can be read from this page, which has been brought in from secondary memory. Now is it clear to you? Anybody who is not able to understand this concept?
Sir,
Yeah.
can you just repeat that part, that how will it take 1 million cycles and when it will
Okay,
take 2000
so
cycles?
right now we are assuming everything is there in main memory, right? Okay, this is in main memory or DRAM. This also in DRAM. At this point in time, both are in DRAM. So the number of cycles will, we know that accessing main memory requires about 1000 cycles. Let's say very approximately, right? And then first you will take 1000 cycles to refer to page table, and then once you get the physical address, physical page number, you'll go to this page number, look, do the offset and do the reading. That will take another 1000 cycles. So approximately we can say in the order of 2000 cycles it will take for simple reading of word for instruction load word. All right. And when we said if there is a page miss or page fault, as we have seen earlier, because there was a page fault in previous stage here. Now where are you going? Now you have to read this from where? This is in disk, and disk is at least 1000 times slower than main memory. You can read actually. I mean, we have seen in the case of hierarchy, right? You can see, you can find out exact value, how many times, find out the fastest disk now, and look at the fastest DRAM and see time difference, right? How many, what is access time? So, so when we said that we have to bring the whole page to main memory, then it's going to take close to 1,000,000 cycles. All right, may not be exact 1 million, maybe slightly less or more than 1 million, but in that order. So what I wanted to emphasize is that the penalty of missing something in main memory is just huge. Now, had we look at other aspect of it, right? See, we have in program spatial locality and temporal locality, and we have brought 4K bytes. It's quite a significant size. Okay, so once you have brought in something here, that the good possibility the next time there won't be miss. All right, so that's the reason, had we had this page size been very small, let's assume 10 bytes, then there's a good possibility the if page size being very small, uh, there will again a miss. All right, so that's the reason, and another reason why page size is larger is basically at one time disk can transfer huge amount of data. So every time if you have to transfer 10 bytes, then it may take, because access time remains the same, right? Whether you transfer time is hardly any, right? This depends on the speed of disk, but in general bringing more data together is better because of the locality reasons. So there have been a lot of simulation study what is the ideal page size. Okay, considering the virtual address and physical address, physical memory size and virtual memory size. Okay, is it clear?
Yes, sir.
Okay, all right. Okay, so this we have already studied. So what happens is then when something is missed, then we have page fault. As soon as page fault happens, then OS routine called page for handler is brought into the picture. Okay, so here, for example, as a result of some instruction, say for example, we are running this instruction, move from some memory location, bring the data to some register, and then this thing is not available in main memory, so page fault has happened. Okay, as a page fault happens and page fault handler is brought into the picture, control goes to page fault handler, which is actually kernel routine. Okay, and then one exception is raised, of course. So now what it does is that it will do the function of bringing that page from disk to main memory, and once that is over, it will come back to the same instruction, and this instruction will again start. It will again read this location, and now this page is available, and so there will be hit, and we'll get the word or whatever it's getting from that location. All right. So note that we have used a word called demand paging. Now, demand paging means that don't bring the page from secondary memory or disk to main memory or physical memory until it's required. Only on demand, when program instruction demands that address which is not there in main memory, in that situation only bring it from secondary memory. That's called demand paging. Okay, we also call it swapping. Okay, so basically demand paging is a strategy of waiting until last moment to swap the page when a miscall. Swapping is nothing but bringing something from disk, a page from disk page, bring it to main memory. That's called swapping. Now swapping can be both ways, right? Swapping in is bring it from disk to main memory. Swapping out, a page is swapped out, it means that it's brought from main memory to disk. Swapping in and swapping out. And demand paging is that don't bring it a page until it's required from secondary memory to main memory. Now this is the most of the machines use demand paging. Now other method is also is that once you're starting a program, you know what all is needed, right? So based on program behavior, bring those pages from secondary memory to main memory right in the beginning. Okay, so these are prediction mechanisms. So, but we are not uh, studying that. It actually is not also implemented in most of the machines. All right. Now let's move to the next topic. Okay, any question up to this point? Is it okay? Okay, all right. So assuming that you have understood, and let's move ahead, right? So now this is what we see here is a page table. Note that page table corresponds to each process. Each process has a page table. Okay, and we know that different processes have different permissions. Some are kernel processes, some are user processes. Some processes have read permission, some have write permission, some have execute permission. You must have seen that also in with your files that you create in secondary memory. There's always a permission, right? What permission has, right? Uh, so we can now set this permission right in the page table. Okay, so we have, for example, this entry in page table. Okay, this corresponds to say virtual page 0, and then we have, of course, we have mapping here, physical page number, and apart from that we can have 4 permission here, whether this whether kernel mode is allowed or not, or supervisory mode is allowed or not, right? Okay, so for example, a user process may want to get into supervisor or privilege mode and do something. Now, whether that user process is allowed to go into kernel mode, which we'll study, of course, in next semester, that permission can be set right here. So whenever user is trying to get into area which is not supposed to, then a trap can, exception can be raised by memory management system. Okay. Second permission is read. It means that this location which is pointing to, or this page, the user or process I is allowed to read this or not. Okay, second is write. This process is allowed to write in any location on that page, and third is that this process is allowed to execute something. Okay, so these are the 4 permission that we have set. Similarly, for So each process will have page table, remember, and then for each process the permissions can be set right there in the page table. And if process is violating that, for example, there is a the read permission is not there, suppose, or also a write permission is not there in this case, right? And then execution is of store word to contents of some register one at location, say s2 whatever location, right? Now this location obviously is corresponds to this page, and then this instruction is trying to write, and this says that no, it's not allowed. Then this point in time, memory manager can raise an exception. Okay, and then of course OS will be notified and something will happen. All right. Okay, any question? No question. All right, so let's move ahead then. Let's take few examples. Okay, just to illustrate the point, although it's very simple, so but I thought it's good to include some of the examples. Okay, so let's assume the virtual memory size is 2 GB, which is 2 raised to 31 bytes. Okay, we have not used 32 here, just 31. Okay, just for this is an example, this is not the real scenario, right? Just to illustrate, physical memory size is 128 MB, that's 2 raised to 27 bytes. Page size is 4 KB, which is 2 raised to 12 bytes. Okay, so virtual address space, obviously you have 2 raised to 31 bytes in address space, so obviously you need 31 bits to represent virtual address, right? Now physical address is 2 raised to 27 bytes, so address will be represented with 27 bytes. So we will have, out of say 31 bytes, you have 27 bytes to represent, I'm sorry, 27 physical address is of 27 bytes, I'm sorry, and the page offset is 12 bits. So offset page size is 4K, and the within page location is represented by this 12 bits. Okay, and number of such pages in address space will be 2 raised power 31 minus 12, that is 2 raised power 19. So this will be 19 bits. So this will represent a page in virtual address space, or actually it will point to a location in page table. Okay, and then if this page is available, then this number of bytes that we need here is that corresponds to one of the pages, right? So one of the pages means that it will be 15 bits will be here, and then offset from here we'll go to corresponding page number in physical memory, and then from here we know the offset. Okay, so starting this at the offset you get the exact whatever you want to read. Okay, so it's shown here, this is a virtual address starting from 0000 and then up to 7FFFF. Okay, and the physical address is correspondingly shown here. Okay, and then of course we need a table for this one. Okay, so let's assume that we have something called a section is being executed, load word, and then say S1, and then we have something S whatever, so this corresponds to this number 0x000247C. Okay, so this address is generated by pipeline. Okay, and then this word is to be read. Okay, or maybe let's assume that is a load byte, so this byte is to be read, which is at this location. Okay, so now we know from this one the offset is 12 bits, so these 12 bits in this address, essentially each, note this is hexadecimal, So these three hexadecimal represents actually 12 bits. So this 12 bits is page offset, and then virtual page number will be 0002. Okay. Uh, all right. So and then we'll take this as an index to look at the location in page table. So 0, 1, 2. Second, the third entry will be looked at it, and from this we get the physical page number, right? So we'll get here the physical page number. So we'll take this as a physical page number and add, and then this 47C that we are getting an offset is added to this one. So this gives actual physical address. So physical address that becomes, it becomes 7FFF47C. Okay, is it clear?
So could you please repeat once again?
Okay, so tell me what you couldn't understand in this one.
So the mapping from the virtual to the physical address 07 FFF.
Okay, 0. So basically what we have seen from this one, we know where to go in page table, right? This points to, this is first, 0th, first and second position. So we know we use this as an index in the table and go to this page table entry, this PTE. And in PTE, we have seen it has a valid bit. And of course, we can have security bits, which we are now ignoring. And then physical address, physical page number. Okay, so this gives physical page number. From here, you read 7. It means the physical page number is 7FFF. Now you go to physical memory and go to this page 7FFF. Now 7FFF gives the beginning of the page number or physical page number, right? It's the beginning location of physical page number. Sorry, I'm sorry. It gives a page number. So when you use this an index, assuming that it's a 0, then you go to beginning of the corresponding page number, and then you have offset available from 47F, and from there you go to 47F location, right? It's a byte addressable memory, so you just add to the starting address that you get it from page number, and then add to this offset, you'll get corresponding location that you want to read. Okay, or you can think in this way that you get physical page number from here, append to that offset, and now this is physical address available to you. Because this will point finally to a page, physical memory, to a particular page. Okay, so this page will have address 7FFF and maybe some zeros, then maybe 000. Okay, and then here you add 47 this offset, and then this is 47C offset. It means that 47C location, you convert this to 0 and then keep moving down, assuming that your sorry, I'm sorry. Okay, up. Okay, and then you can read this one, assuming that this memory is going this way. If that is not, then this will point to the bottom of the page, for the starting of the page, where starting location will be 7FFF000, and then go up to 47 display terminal and read that. Okay, I think you need to just this reason I have requested you to do some homework at home, because you need to absorb all this, right? That's another example. Okay, so virtual address is 7F20. This is physical page. Okay, physical number. So what we do is that okay, I'm sorry, this is a page table. Oh, I'm sorry, this is a page table. And the entry inside gives a physical page number, right? So you look at here, this is a fifth 00005. So you go to the fifth page, or use this as an index to point out to the fifth entry, and each entry corresponds to a page. So 1, 0, 1, 2, 3, 4, 5. And from there you read the physical page number. So this is the one here, and from here, because page for physical memory and virtual memory is of same size, which is 4K, and take these 12 bits, and then this gives append this to physical page number you received, so you get the complete physical address. Okay, all right. So it's very simple, extremely simple, right? So I will request you to kindly read this again. Okay, now next thing is that where this page table located. Okay, page table we know is in main memory, but some its location should be given by something, right? And we call this is called it's called a PT base register, okay, or page table base register. This base register for when process in execution and doing some referencing, then PT base register will give you for that process starting address of that table. Okay, all right. All right, so kernel page table containing entries of okay, all right. So we'll look at this second point. So this is it. So we have page table base register. So far we have not bothered about where the page table is starting. So we have page table base register which gives the starting address of the page table for that process. Okay, it's OS operating system's role to load this page register page table register appropriately. Okay, and then this is the virtual address that we get from process. Say for example load word. Okay, whatever address is there we look at there. Then we have VPN virtual page number. Based on virtual page number we come to particular location or particular page table entry. In that entry, if the V bit is 1, it means that we have a hit. Then we get physical page number from here, we read it and get offset from here, and then we have physical page. All right, so only difference is that here we have starting address available. Now where OS will keep track of all this, because there are n number of processes in execution at a time, right? So there is a data structure that's called kernel page table. Okay, so now what happens is that as the process is starts execution, this OS will look at kernel page table, which again is pointed by another register called kernel page table base register. Okay, and in this one we look at corresponding process ID. For each process there is a location. Okay, for page table, because each process has a page table. So this page table address is kept here. So there is multiple referencing, right? I mean, for example, as soon as this is used, then we'll look at page table base, and then we'll know from there where the page table is actually starting. Okay, and then from the page table, let's assume page table is starting here, then use the translation to find out which particular physical address we want to read, and then once we know that, we go to actual physical address and read it. So you can see number of steps really required in simple read operation, because there are multiple data structures involved. For example, there is a page table is involved, then some data structure that will tell that where the page table is beginning, that is in the register. Then this register is to be loaded from some position. So there must be table corresponding to each process, where each process page table actually starting. That is, and that's what we will call as kernel page table. So kernel page table is also in main memory. So now you see number of references are going up, right? Just to read a word. All right, and all this needs to be optimized. Any question? Okay, all right, let's move ahead. Okay, so this part we have already seen. So now let's look at the number of steps that are needed, right? So first step for the page hit. Now I have brought in these slides because it gives the flow, so you shouldn't have any confusion at the end. CPU generates virtual address. Remember that, you know, the pipeline, whatever load store we are doing, it generates virtual address. Okay, corresponding to address space. Okay, and it's intercepted by memory management table. Sorry, memory management unit. Okay, and then what it will do? It will fetch the page table entry from the main memory. Okay, so it will look at virtual address, virtual page number. So virtual page number, it will, and this page table is there in, for this process that's running is in memory. So it will then page table entry, it will check. Okay, and all right, and then if it is available, if there is a page hit, okay, then this page table will be brought in, and that entry will be brought in, right? So what is the entry in page table corresponding to this VPN number? We have physical address, physical page number, and then okay, that's all. And validity bit is already there, that's the reason it has come back here, right? So what is the next step now? It has got physical page number and it knows the offset, because this offset has come from here. Now it will go again to a location in memory and read that. So it will now request for particular physical address. Okay, and then respond will go back directly to the CPU. So it's clear. I will show it again. First request comes from CPU, for example, load word with some address. So this is a virtual address, and then it will be intercepted by memory management unit because this is not the true physical address. Then this virtual page number will be sent to by memory management unit to corresponding page table. So let's assume page table is here, it will be sent, and then if it's a hit, then that entry, which is physical page number, okay, will be brought in here. Okay, now, okay, now append to this, it will now, from this it will know actual address of the physical map location. So that address will be generated because physical page number is known, physical page number plus offset is the address. So it will send this address to cache, to main memory, and main memory will respond back with that word, that load word, you know, whatever load word wants it to read at that location, whatever is there will come back to CPU. Is it clear? Is the flow clear? Pavitra, can you take the attendance again? There's some 5 people have gone.
Yes, sir. Okay. Yeah.
Okay, I really don't want to be tough, but I really want to understand why. I mean, if they're not able to understand, then I can repeat it 10 times, but they need to focus. All right. Any question? I'm asking Sudarshan, are you there? Sudarshan, are you there? Okay, let me just note down his name. Okay, I'll remember. Sorry. Virenj Patel.
Yes, sir.
Are you able to understand?
Yes, sir. Somewhat. I mean,
Somewhat, or are you? What you couldn't understand? Tell me.
sir, I'm getting some of the things, but I mean, I'm not confident about that. That's
No, but you know, something you understood it, something you couldn't understand, right? What I want to know, what you couldn't understand. Because I brought in so many diagrams wherever I could get it. I brought it just to make it very clear. And what we are studying today is same that we studied in the first class, right? Yesterday. There's
Yeah.
nothing more. Right?
Yeah,
Nothing
sir.
more. So I want to understand what you are not able to understand.
Sir, I mean, not that much I'm not getting, so I'm
No, but
getting all the things,
you
I
understand
guess.
what is virtual memory?
Yeah, sir.
What is it? Okay. I am failing in teaching. It looks like, if you can't understand the basic things which are repeated 100 times, somewhere or other, I think it's my failure. Okay, maybe I will ask somebody else. Okay. अरे चलो छोड़ दो. Okay, all right. Okay, let me just finish it off. All right, in case there is a page fault, CPU always generates a virtual address. Okay, in case of page, and request comes to memory management unit, it will ask for whether virtual page number is available. Then virtual page number will be checked here in memory. And then if that is not available, so that entry will be returned, and memory management finds that that is not available. Then it will say that, okay, now I will request OS. It will raise an exception to OS, and corresponding page fault handler will come into picture. And it will now, if this memory is full, what it will do is it will first find out which page to replace, and which it finds out some page is called victim page, and if victim page is dirty or it has been returned, then it will go to memory. So it's basically it will be returned in swap space, and then the page which was not there will be brought in to main memory, right? Okay, now again there will be request made. Okay, next step. Okay, and then this page will come to CPU, right? All right. So basically, if there is a page fault, then it has to find out which page to replace that, and the new page, something that's missing, will be brought in from disk to main memory, and then again, the same read will happen. Say when we are doing, say, load word, and then it will be hit, and then that particular page then will be brought to CPU. That's it. It's very simple. Okay. And now we can combine, integrate both virtual memory and cache. So far we have not discussed cache. Okay, we said that there is a disk slash cache, or cache or slash memory. Okay, now we show them separately. Okay, so now there's a request for virtual address, some address CPU request. It will be intercepted by memory management unit. It will know virtual page number from this request. Virtual page number will be looked at. In where it will be looked at? It will be looked at in cache, because we are assuming that page table is now available in cache. We'll see that how page table can be brought into cache. Okay, and then if this is a hit, it means that this page table is available. Page table entry corresponding to this address is available. Then this entry will become here. It will read the entry, and okay, so from this it will come to know physical page number, and then it knows the offset. So it knows the physical address. So this address will go here. Okay, and if this address that we want to read is also part of the cache, it will be, because cache also work for data, right? Now we are know that the cache we have brought into the cache page table, a page table also, right? So if that's available, it means that there is a hit. Okay, so that data is, if this address that we are requesting okay, is available here, then there's a page hit and this data will go to CPU. Okay, if there is a miss, then it has to be brought, okay, then it has to be brought from disk to cache. Okay, now one scenario we have not seen, okay, one scenario was that, you know, here we are making page table entry address when we are giving what VPN, virtual page number, and if we assume that page table is available here, if it's not available, then there will be page table fault, so it will go to main memory to fetch that page table. So now page table comes here and next time there will be hit. Okay, all right. So once there is a cache, then everything has to be brought to cache, and then again reading request will happen, and then data can go to appropriate place. So that's all we have. That's the advantage of cache. Now with the help of cache, you know, overall time to read a word, right, or a byte, say load word or load byte, will reduce significantly, right? All right, so in this lecture we have seen need of address translation table. Okay, and then we have seen that if virtual page is not available, there is a page fault. If there's a page fault, then page fault handler comes into picture, which brings the virtual page from secondary memory or disk to main memory or physical memory. Okay, and then we have seen the page table. If page table resides in main memory, then time to access page table itself is 1000 bytes. Why not bring the page table then to cache? Okay, so first thing, when virtual address comes, the memory management unit will send that virtual page number to cache and cache to virtual page table. Okay, if that available, then it will return page table entry, and from there you can find out physical address, and then you go to cache. If that page that we wanted to read from main memory is available in cache, fine, you read it. Otherwise, bring the page from disk to main memory. That's the overall sequence. All right, any question?
So I had a question.
Yeah.
So the page table that is brought to cache, that will be dependent upon the process, right? So there'll sort
Yes.
of be a mechanism that if a process changes, then change the entire page table in cache.
Yes.
Okay, so
Everything is same. Everything remains the same, right? Whatever the function of cache is exactly same as that for data we have studied earlier. Note that page we are not bringing the whole page table again. Page table again can be paged. Okay, on relevant portion can be brought in here, because you know each page table entry represent a page, which is itself is 4K byte, right? So just few page table entries per process are generally sufficient. That we'll study in the next class.
Excuse me, sir.
Yeah.
Sir, I guess Sudarshan is trying to talk to you in the chats.
No, that's
Can-
okay. You know, it's his choice to be alive in the class or not. You know, all you can as well watch match. It's your call. Like, you know, after all, you know, I can't say. I mean, if he's there's nothing I have to say. Only thing is be attentive. That's all I can request. It's for your good. All right. Okay. Thank you.
Thank you, sir.
Thank you. Bye bye.